Great. Okay, thanks everybody for coming. We're going to talk about semantic and its analysis, private data cloud, and how its products help make things secure. I'm Steve Brodsky. I'm leading the analytics for the Cloud Platform Engineering Group, which is Semantic's private cloud. And here with Daryl.
This is on? Yeah, hi, I'm Daryl Kinsley. I'm from the Semantic Herndon, Virginia office with managed security, doing managed security analytics.
Okay, thanks. So one of the first things we'll talk about is why we have a cloud and what we're doing with this all open source cloud. We call it Cloudfire as the code name for Cloud Platform Engineering. And this is where we're doing all the big data technologies that we've been talking about at the conference. And one of the other important things is then what are we offering? What are we doing with the data? What is all this security data that we're using? How are we using it with products? A lot of people know about several semantic products. The most famous, obviously, is Norton Antivirus, but there's obviously a lot of products. And all these products are working together to share this cloud. And what we're doing is we're applying an all open source approach towards making the foundation of this cloud work. We have been extending open source with a lot of administration and monitoring, and also we'll talk about some of the work we've just started with Hortonworks' new initiative around dynamic clusters using Cloudbreak. So the first thing is sort of extending where we had in a panel discussion this morning. There were several people up, experts, DTL is representing our semantic cloud. And in this semantic cloud, what happens is you have a lot of different products, and the products are actually related to each other. They're not just point products. They actually share a lot of the same data. And what you'd like to have is products where when you detect a threat with one product, you'd like it as fast as possible to help safeguard everybody else who's using the other product. So in a sense, one overall integrated security system. Now, in order for that to happen, though, you'd need a very large system that runs at scale using a lot of the technologies we've been talking about. So how we do that is we have been building the next generation of cloud. All the products really are in Semantics Cloud, but we're building an all open source, very powerful, efficient cloud based on two main sections of technology. One of them is OpenStack. OpenStack.org is a whole ecosystem, much like there's a Hadoop ecosystem around Apache. There's an open source ecosystem called OpenStack, which is primarily around the idea of dynamically creating your own virtual machine environments and managing the networks, managing the access, managing the quotas, managing security for how all those virtual machines are used. So between virtual machines, which are managed by OpenStack, as well as the management of metal machines, we have a dynamic, horizontally scalable cloud. And in addition, we have, for a very large portion of that cloud, an interest in using those, the cloud resources for doing analytic processing. Think about the analytic processing. There's a lot of data that has to be streamed in from many devices, and we'll talk about what some of those devices are and how we process the data. These are coming in from different gateways, different servers, different products, whether it's from mobile. People are very familiar with laptop-based systems for antivirus. It can be from data centers. It can be from networks. Some of the capabilities of all the different aspects of the computer system, they're all streaming in data, and they all need to understand what's safe and what's not safe. So obviously, to do a lot of that processing is the analytics software that we'll be talking about, which of course is all based around the overall larger Hadoop ecosystem. We've been partnering with Hortonworks as the main distributor and distribution that we're working with, and we've been working very closely both with them on the current set of products and also some of the latest things they've been announcing in this overall system conference. So by combining an all open source base with the Apache Hadoop system, then we're able to address some of the main questions that are around security, which is, first of all, how do we support the ability for all this analysis to happen? So one of the first questions is do we have the data to actually go and perform the analysis? And a lot of people have talked about the importance of big data. So we actually have, at petabyte scale, access to the key data that is streaming in from multiple endpoints around the world. And this enables us to perform a lot of calculations at high speed. So can we do the analysis of the data? Well, one of the most important things is to bring the open source analytic engines to bear, whether or not that's the traditional Hadoop MapReduce, the very popular Hive SQL, or some of the newer technologies around Storm and Spark. In particular, how Storm and Kafka are used together to provide a high performance streaming engine that found as the basis of what we call the analytics pipeline. It's an industry standard pattern of processing a lot of information at scale. And then what we're doing is we're taking analytics which may have been happening in long time frames and bring them down to the second range so that when threats are happening, they can be detected effectively in near real time. So a high-level diagram about how we put the overall system together. We are taking in this telemetry data from many different endpoints, and we're streaming it through what you're seeing as the data transfer arrows, which is a variety of different techniques to bring data from the incoming gateways into the clusters that we have built. We're using different kind of data importers, and in particular, Kafka is extremely important because that allows high-speed, scalable, parallel, log-based processing. That information goes into our various different clusters. The clusters use all of the traditional open source technologies, Storm for processing the Kafka queues, some of the newer work around Spark. We use Hive and SQL extensively. And then, of course, the results are both stored and processed inside the overall cluster, managed by, obviously, Yarn, and data stored primarily in HDFS. Multiple products use this. They take this information and results in real time, whether the real time is coming out from HBase, Elasticsearch. Also, Kafka is a great place to stream out your analytic results. Those are used by the products, which can then provide analysis results to users, either in terms of real-time protection or in terms of advice and recommendations to people on how they can make changes to their own systems so that they'll become more secure.
So Steve asked me to come talk about this one product that we just, shipped, for lack of a better term. This is a services project that a legacy product that's been running for about 15 years, hundreds of external customers. These are our enterprise customers that trust us to secure their networks for them. We have been processing these things traditionally through SQL servers. Does this thing work? Oh, sorry, I pressed the wrong button. Is there a back button on this thing? There. Sorry about this. Technical difficulties. So we have Bastion hosts that receive data from customers. We process it on a local importer system. Today, or yesterday, this data was being copied directly to a series of SQL servers where our analytics were being done on legacy systems running on SQL Server. SQL Server is not the best platform to do analytics on, but it worked. And it was a running system that's been running for over 10 years, and we've amassed a great deal of customization, tweaking, and customer-specific knowledge there. If a customer tells us they don't want to be alerted about a particular event, they don't want us bringing a new system in, forgetting all of that history, and starting to alert them on all the things they've told us not to alert them on before. So the goal of this new system was to greatly improve our performance. In the keynote this morning that talked about this pyramid, we could see this as the thing that the CIO pays for to just make it faster. But the truth is, it's not just making it faster, it's making it more flexible, it's making it more reliable, it's making it more able to support new types of analytics that we can't run on SQL Server. Our hands were always tied because people would want us to try new things. we'd say, well, the data isn't in that format, in that place, we can't do that. So this new architecture is tremendously flexible, and it's running in production today. This project took us about 18 months to get from concept to running 40 billion logs a day for enterprise customers, replacing our existing system. So it's been very successful. Give you a few more details about this. We chose Storm for this project. As you can see in the graphic here, we've inserted a new product here we're calling QStuffer, which loads data into Kafka, and then from Kafka we can process it in the CPE data center. We can do all our analytics on it there, and then push it back into a new component to pull stuff out of Kafka and reloads it into SQL Server. But now instead of copying 40 billion raw logs into SQL Server, we're copying a few 100 million alerts per day that have already been processed, where we do all the analytics in the cloud instead. I wanted to say this is not the Lambda architecture. The Lambda architecture, as we've read about it, talks about, we can do everything in batch, and then, streaming will give you the deltas in real time. But if you make a mistake, that's okay, because we'll rerun the batch, and then we'll correct all those mistakes that we made. And if we wake somebody up at 4 in the morning, say there's something wrong with your network, and they go to log in, and the next batch job has run and cleaned that up because we made a mistake, we don't get those kind of do-overs. This is our architecture. It is a streaming architecture. We know we want to be able to do some new type of batch analytics, so we have a Kafka queue, and one of the things that CPE is going to be giving us is the ability to load that Kafka queue into HDFS, into batch. We can add new batch jobs that way. But for now, we're looking at Storm primarily. We chose Storm because it was very, very, very flexible. Tools like Spark are very elegant if you want to run the same code in batch and in streaming. We did not want to do that, and what we wanted to do was try to bend Storm in ways where it really was never intended to be worked with. We had this prototype. We were working with Hortonworks already. They sent Taylor Getz, who's like the primary contributor on Storm, to our Herndon office. We met with him. We said, how crazy are we? Will Storm support this? And he gave us a couple of little ideas, but basically said, no, you're not insane. This will work. You've got everything covered. And so we kind of like crossed our fingers and whistled past the graveyard and went ahead and built it. And it was great. It works. And a lot of our concerns about the early Storm, and particularly the Storm Kafka spout, were not the most mature thing 18 months ago. We raised that with Hortonworks. Hortonworks turned around. The next thing we know, the Storm Kafka spout has been adopted into the Storm mainline. They're improving it. They're fixing it. They're adding stuff. They've been great to work with in that regard. So I wanted to give a couple of little lessons learned that we found from doing this project that might be of use to people who are thinking about doing something similar, taking an existing legacy system and trying to move to Storm. One of the things was, very early on in the process, we figured out how to T our data. The current system was loading the data into files, and we built a little program that could just sit, watch those directories where those files were, grab them and stuff them into Kafka. And it wasn't reliable. It didn't get all of the files, but it got over 99% of them. And it allowed us to start experimenting at production scale with zero possibility of impact on the production systems. And I think that's really key. We had this thing running at production scale for over 12 months. And we got to see and tune the system and really live with Storm running day in, day out, where it wasn't on our critical path yet. And we took the data coming out of our system and we compared it to the existing system that was still running and compared the two, and really did we had an oracle essentially that allowed us to see if this complex piece of software that was radically different design from the old version was still producing the same results. And it was, except when we found bugs. More often we found bugs in the existing system than in ours. When you had the opportunity to have two different versions of code that are supposed to do the same thing, you start finding things that you didn't realize were there. Another thing I wanted to mention, I didn't press that. Another thing I wanted to mention about Kafka. Kafka is wonderful because you can load data into it, and your producer can continue to run, putting data into Kafka, and if nobody is taking data out of Kafka, it will not back up. You will just continue to load it into Kafka, and eventually it'll fall on the floor. Kafka will reclaim that disk space. You don't have to worry about your pond filling up, your drives filling up, and things falling over. You just keep loading into Kafka, and Kafka will reclaim that disk space. And this really allows for what we're looking at as grassroots collaboration. There's a lot of groups in Symantec that have data that they'd like to share with other groups. And rather than figuring out a tight fit, here's a message queue, I'm going to push data to you, and if you're not there to receive it, my system's going to fall over or start blocking. Well, with Kafka, you can just spew data into this queue, and if somebody wants to pick it up, they can. And if nobody picks it up, or if those consumers fall over, it has no impact on you loading data into that queue. And if other people want to subscribe to that data and start taking it, there's very little extra overhead from having multiple readers on Kafka. So it's a really nice, loose coupling between systems that allows for this kind of grassroots collaboration. One other thing that DTO mentioned this morning is that we are doing more anonymization. And one of the things that we're doing in this system, on this Storm cluster now, is standing up an anonymization topology that can take our customer data, sanitize and strip all those potentially sensitive things, and make it available for sharing within other groups within the organization. So that we can try new analytics. We can have our friends from the research labs who maybe are more interested in publishing papers, but we want them to be able to have some really rich data to work with, just not anything with anything customer sensitive in it. So having an anonymization topology there, allowing us to try all sorts of new things, giving, we talked about governance and why it's important to protect our customers' data. This is another really useful thing. So the takeaways I wanted to mention here is that Storm is extremely flexible. If you haven't used it before, I think Dave said perfectly this morning, jump right in, forget your fear, just start building it. You can build on a single JVM local laptop. We've downloaded temporary anonymized files, run them on local laptops for our first initial development cycles. You do want to always test, and particularly test performance on a real cluster. You get in a lot of trouble if you extrapolate from how something runs in a single JVM to how it's going to run on a cluster of a lot of machines. Not speaking from experience there or anything. One of the challenges with any sort of streaming system is that the system is constantly running, constantly changing. It's very hard to go back and figure out why something came out the way it did, unless you have all the inputs and you know that there's absolutely no timing discrepancies there. And we have a lot of timing discrepancies. If new feed data is coming in real time, new threat data, we want to be able to incorporate right away. Well, it's hard to go back and say, well, our system generated this alert, but the legacy system didn't. Which one was right? Well, what was the feed data at that exact moment in time? We don't know. So it's challenging. If you can run your Storm topologies on a local system with local files, design your frameworks so that you can use local files when you want to run and test in a controlled fashion, but then flip over to production where you're pulling down the actual feeds. That was a lifesaver for us. And I guess the only other thing is that everything when we launched this, because we had so many months of running the two systems in parallel, it really went out to a flawless launch. Storm got a very, very good reputation within the company for this. There's a lot of people coming saying, we want to do our stuff in Storm now because it's so awesome. The only thing that went wrong was that apparently there were some problems because now these systems were so unburdened. They were running other processes too quickly and too frequently. They had to throttle the rest of the system because Storm had taken so much load off of the SQL servers. It was a good problem to have.
Thanks. So that's one of the great things about doing the big data software is it gives you new flexibility, ability to do things better than you were able to do before, and also as a result of having all the data together, what you're seeing is the access to that data allows new analysis, new insights, and Symantec is actually introducing new products based on the ability to have all of this working in one place. Now we have multiple clusters that are running out of OpenStack, and the point is that some of these clusters are shared between products, some of them are unique, some of them have the ability for the data to be moved between products, and some of them can share the same data. Kafka and HDFS are two of the great ways to help combine systems. Now, we run multiple clusters, and that means that we have to make sure that the systems are all up, the systems are all administered and monitored, and the systems all contain the key engines combinable in the right fashion so that people are able to do their analysis at scale. And one of the things that we're showing, for example, is last year there was a presentation at the summit about how one extremely large data lake was implemented using traditional relational database software. And it was okay for, in a sense, its time. But the scale of the data went up, the scale of the need for processing quickly went up, and so effectively we've been taking it on a journey where the project that you heard about last year has moved now entirely to leverage the big data technologies, and then we are also taking it now into streaming, and so this is also another set of projects which have moved forward. The pattern that most of them use is a pattern where data sources, for example, the telemetry coming from antivirus or other detectors in the world, are sending information saying, this is happening in our systems that we're monitoring, and that analysis happens then streaming as each event arrives. For example, somebody is having their server access a particular URL, they're accessing a file, they're doing some access. You want to see, is it right, is it not right? In the language of the data science, this would be effectively scoring the data in the streaming analysis. The batch analysis would be computing effectively some of the next sets of targets, what's good, what's bad, what's safe, what's not safe. Actively available results is the ability for people and machines and products to leverage all the information that's been made available, find new problems, and also online access, so that every time access is happening, the machines all over the world can now get the latest information about those files, what's safe, what's not safe, and have that information immediately available from multiple places around the world. So the combination of the ability to assemble these applications quickly and leverage and share data across multiple systems leads to the ability for people to be able to really leverage this data much faster and much more efficiently. Now, as I was mentioning, this requires a lot of different kinds of engines. So effectively, we've deployed almost everything that's in the Hortonworks distribution, plus some more things as well. And one of the ways we do that is we really leverage Bari very heavily. Even though there's a certain amount of capabilities in Bari based on these are the servers that are installed. And as you can see, Hadoop, Yarn, Storm, Uzi, Hive, Pig, SQL, Pig, Uzi, Kafka, HBase, Spark, all these are managed and deployable via Bari, but we've also done is we've extended it to do some new services as well, including some of the custom ones that we have on our own. Then we also have, of course, a variety of administration tools, and these administration tools, that laser pointer and pointer combination is quite interesting. So the point is that we'll talk about some of these administration tools. What happens is when we create a cluster, we want to automatically create the cluster and all its administration and all its monitoring all together simultaneously and manage that. We also have a number of data science tools. Some of them are in the relatively earlier state, but we're also early adopters of Bari Views, which is a new capability for adding some interactive work with things like what's popularly known available in Hue is now being effectively redone a little bit better in Bari as Hive SQL views and job browsers and file browsers. And we've been extending the Bari views ourselves, and I'll show some of the ways we've been doing that. So what you see here, first of all, is one of the clusters. And you see that what we've done is not only leveraged it in this particular cluster, it's running multiple petabytes, has several million files. You can see down in the corner, 3.5 petabytes of data loaded in this particular cluster. And it's kind of scrolled off the bottom, about 10 million files. That's just one of the examples of a data lake with a large amount of shared analytic information. And then you can see a number of the different services that are available in this particular cluster. Now, in addition to this regular Bari function, we've then added to it. So one of the things that we've done as an example of an extension to Bari is Bari has custom services where you can build what's called a stack. And you can add any different kind of software to that stack. We use it for adding our own internal components and web servers, as well as this example here is adding Elasticsearch. It's a pretty popular capability that people are interested in having with Hadoop. So by adding Elasticsearch as an Bari view, an Bari service, it will install, it will start, stop, smoke test, and that all happens because Bari has a framework with a plugin, and all you need to do is implement the plugin for any particular server that you want. In addition, then it can also unroll other things like the user interface. Now, we have added a number of different services. Another thing that we have added, a recent open source contribution, is Bari iframes. So even for servers which were never actually aware about Bari, we can use Bari as a single entry point for accessing all the open source UIs. And so this is an example of some of the open source UIs that can be made accessible just by plugging in the iframe to Bari and point them to the appropriate servers. That was a UI of Storm, Storm's Nimbus UI, the administrative console for Storm, as viewed via Bari. Cluster usage is very important, as you can imagine. When you have this much data with several hundred users being able to access it, it's quite easy for those users to access it in an inefficient fashion. So we've been using a variant of the software which is related to Hortonworks' new announcement around SmartSense. And this open source software allows you to analyze what has been done in your cluster, group it by who's been doing the most access, what could be done more efficiently, what changes and settings need to be improved. And so overall, you improve both the clusters and the users of those clusters. We have also been extending the cluster administration using dashboards. We've created a number of dashboards that are powered off of Bari metrics. What we do is we take Bari metrics, which are collected by Bari. We then run a process in the background which takes those metrics and sticks them into a database. The database itself doesn't really matter. InfluxDB is a database that we have been using for another one of our projects that has been open sourced around the name Volta as part of the overall OpenStack ecosystem. And what we do is we take those metrics, we put it in InfluxDB. We've built a series of dashboards. A couple dashboards here are showing some of the overall availability, some of the overall sets of what's also the reliability dashboard. With these dashboards, because they're based on Dashing.io, another open source framework, you can actually customize and control what you'd like to see. So the idea is you spin up a cluster, you get all the monitoring by leveraging Bari to do the complete set of install, and the metrics collection, and your own custom services to bring up your own custom dashboards. In addition, we use a number of open source servers to determine alerting on whether or not clusters are up and down, servers are up and down. We're using OpsView. One of the clusters here is shown with an OpsView, and OpsView is relatively useful. It pings the servers constantly to see are they up or down at both the Unix level as well as the server level, running out of disk space, and other checks as well. One of the other pieces of open source that we leverage is what's called the ELK Platform. That's Elasticsearch Logstash, and Kibana. And this is Kibana and the Grafana UI, which are both very closely related projects. We use these together as part of the Volta project that I mentioned. And what we're doing is we're monitoring not only the behavior of the network, but also the rate at which data comes into the network. Because you want to make sure from all your different endpoints, from all your different collection places, is the data keeping up? Are you capturing data at the expected rate? And you can see, for example, this is a place where the network throughput was dipping. And we can set up and trigger alerts based on different logical conditions. This is showing the transfer rate of where a particularly difficult set of connections. So we can see that, that in this particular case, some of the network traffic was going quite smoothly, others was encountering problems. And you can very easily select and zoom in based on this UI to find out what's the underlying cause. We also are capturing all the logs through the Logstash and available through a Kibana UI, which enables you to quickly search. So it's just another case of how we're using the overall open source ecosystem to build automation. And one of the last things I want to mention in the last few minutes is how are we working with the open source community to attempt to make it so that not only can we spin up clusters dynamically, but that it is actually easy for anyone who wants to do their own dynamic clusters. So what we're doing is we were on a path where we ourselves are working on creating clusters by a combination of going to OpenStack, which is our private cloud, as we already know. You can go to OpenStack and request a series of VMs. The VMs are then installed with new software. The software installation process is basically the regular Bari process. We unroll RPMs. The RPMs have the Bari agents. We run then Bari itself and then use regular Bari install from an Bari blueprint. This enables somebody to very quickly stand up a new cluster if they've already got a nice blueprint. And if the blueprint is set up so that all the different aspects of both setting up the cluster and all the monitoring and administration is automated. So we were going down the path of making this relatively important integration happen when working with Hortonworks. They were also working on a path for a project about how can they make a general purpose system that will work with multiple clouds called Cloudbreak that they were announcing at this conference. And Cloudbreak enables you to do pretty much a combination of using Bari with private cloud or public cloud. Most of the focus of that Cloudbreak had really been focusing on was the open clouds, public clouds of Amazon, Google, and Azure. And they did have some work going on with OpenStack as well, which is great. There's an opportunity for us to collaborate also with some other companies that are interested in doing this on providing plugins based on the different providers. And so we'll be working together on how can we make our OpenStack integration and Hortonworks come together. And it starts with spinning up a cluster, and then with sufficient extensions, then we'll be able to make it so that these clusters can come up with all the administrative services that we talked about. So these are screen captures from the Cloudbreak UI. So one of the things that's important in the overall picture is you log into a system. What clusters am I allowed to use? What clusters do I have access to? Can I navigate to one that already exists? Or do I need to go and make a new one of my own? And there's a lot of reasons why you may want to make a new one of your own because, for example, as Daryl's scenario for development, he might want to have his own cluster just for himself to do his own development. That's sort of like a mirror image of the large one, but just scaled down to contain only the resources that he needs. There can be then a series of integration test clusters, which should also be sped up so that the overall set of people working on that product can work together and share what they're doing, share their code, and share how they're interacting. And then their code, as it progresses from there, can then be brought up to the production clusters and then executed there. And so what you get is sort of a family of clusters. Some of them are based on the software development lifecycle, and then some of them are based on multiple clusters that are carrying out different tasks. For example, tasks for anonymization, local data processing, small processing hubs, fanning into larger processing hubs, and we can use all this with a consistent architecture. So one of the things that we are working with Cloudbreak on is to help make this overall multi-cluster goal reality. We have the ability to spin up these clusters, and if you were to combine that with the overall framework from Cloudbreak, we'd be able to have a cluster directory. What are all the clusters that you have? Who's allowed to access it? And all the entry points so that you could, for example, go to your Cloudbreak UI. It shows you your links to the key and Bari views that you're interested in, and then you can navigate on in and see what's interesting about your cluster based on the different roles, whether you're an administrator, developer, or data scientist. So in combination, we're able to really take a whole bunch of open source from many different families, bring it together, and then work with the community to attempt to make some of this available back into the open source community. And in the meantime, we are helping products so that we can help people be more secure and safer as they go about their own work. So thanks very much.